went to corral somebody, but he's standing there kind of waiting for them to come in. So yeah, I think he'll be back. Either that or he figures my voice is loud enough to carry.
We're actually ready. We're ready early today.
Yeah.
We've been delaying the start by 5 minutes.
Okay.
So
We're on time today, or early enough today, or whatever. Okay, yeah, that's fine. Yeah, that's fine.
And it's live now?
Yes.
Okay, all right, perfect.
All right.
Great.
I'll give you.
You give me a brief introduction. Sounds good.
All right. Good afternoon, everyone. Welcome to Colloquium. Today we have someone who I don't think needs an extensive introduction here, all the way from the 3rd floor, as many of you are. So we're happy to have today Dr. Gosky. Dr. Gosky did his undergrad at Miami University, the Colloquium, not the nice one.
Right.
I mean, I'm sure it's very nice. But
Yeah. Thank you.
We're live streaming, so you never have to worry about me going to Miami University or anything. And then got his PhD at NC State before joining faculty here. So anyway, he's going to talk to us today about some of his recent work in statistics. So I'll give it over to Dr. Gosky.
Thank you. Appreciate it. Thank you all for coming on a beautiful Friday afternoon. I know competing with the weather is a challenge, so I appreciate it. So today we're going to talk about some simulation results for Bayesian capture-recapture models that we've looked at with some heterogeneity effects, and we'll explain what all those terms mean, but I wanted to mention this is joint work with Dr. Sankey. A while ago we did some research in this area, and then we thought, hey, if we cleaned this up a little bit and delved a little bit deeper, this would be publishable, and then the referee said, if you do a lot more work and you clean it up a lot more, it will be publishable, so here we are. But they helped us uncover some things that we hadn't necessarily thought of and led to a better final product. So anyways, this is it's technically in press. It's about ready to appear in the Journal of Modern Applied Statistical Methods. So we're going to go through a sequence of steps today. I'm not assuming anyone's familiar with mark recapture or capture-recapture models. We'll introduce those. We'll talk about heterogeneity models. We'll talk about Bayesian statistics briefly to understand how we've done the simulation that we've done. And then we'll talk about our simulation design and goals, what we wanted to show or what we hope to show, what we actually found, and then some general conclusions about these models at the end. Okay, so we'll start with an introduction. So the goal of a capture-recapture experiment is to estimate the size of a population that you don't know. So a size of an unknown population, and we typically call that capital N. It's just the unknown size of the population. And we're going to assume for our purposes the population's closed, meaning there are no entries and exits during the experiment, that it's fixed for the duration of the study. And so the most basic estimator of the population size has been around forever, since the late 1800s. It's called the Lincoln-Peterson estimator. And essentially it relies on two separate samples from the population, each of size little n1 and little n2. And what you do is you take a sample from the population, you mark it in some way that you would know about that element of the population if you saw it again. And then later you come back and take a second sample from the population, and you note the size of the second sample and also the number of marked individuals from sample 1 who showed up also in sample 2. And then putting those, and M2 denotes the number that are captured in both samples, so the number that are actually recaptured. And then essentially the logic that we use in a two-sample case to estimate the population size is we say, well, basically the fraction of sample 2 that is marked should be pretty close to, or approximately equal to, the fraction of the population that we marked in the first sample. And that leads to an estimator of the population size, where we can multiply the two sample sizes together and divide by the number that have been marked or recaptured in the second sample. So we're actually going to do a quick example of this here today, and we'll see if we can estimate the number of people in the room. So first question would be, raise your hand if you are a student. Count the number of students. So 1, 2, 3, 6, 7, 8, 9, 10. I believe we have 10 students, so I'm going to let that be N1. Raise your hand if your birthday is in January, February, March, April, May, or June, the first 6 months of the year. 3, 4, 5, 6, 7, 8, 9, 13. How many of you raised your hands both times? 1, 2, 3, 4, 5, 6, 7. So if I were to estimate the number of people in the room, I would say I would take 10 times 13 over 7, which is going to be, pretty close to 20. All things, I'm not going to do the arithmetic, pretty close to 20, right? How are we doing? It's not too far off, I don't think. It's a reasonable ballpark estimate of the size of this particular room. Now, I knew the size of the room naturally, so why did I do this kind of approach to things? Well, in many cases, we don't know the size of a population, right? What did we get?
18.5 is our estimate.
Okay, and how many actually are there? 21? Okay, so not too bad. Not too bad. So the question is, again, when do you use these kinds of models? Well, most commonly they were developed with regard to wildlife populations, which don't line up neatly in classrooms at the end of a week for you to count them, right? You have to try to figure out how many of them there are. So a common approach is to take an initial sample, like this bird here, for example, and you mark it by putting maybe a tag on its leg, and then you re-release it into the population, and in a second sample, you'll know if you see that bird again by recognizing that the bird either has or doesn't have a tag on its leg. Okay? There can be a little humor attached to this because here are some fish. This fish has already got a fin clip on, and he sees the bait the second time, and he says, well, I said fool me once, shame on you, fool me twice. Hey, what have we got here? And he's going back for the bait the second time. So these methods were commonly developed for animal populations, but people have extended them, researchers have extended them to human populations as well. Cases like how many people are there who are, let's say, drug addicts or have a particular disease in a particular metropolitan area, using lists of individuals associated with maybe treatment centers or different centers that would deal with that drug addiction, and then cross-checking the list to see how many duplicate names there are. And the idea would be, if there's a lot of duplication, then you think you've pretty well got the population laid out by one of the lists, right? If there's a lot of duplication. If there's very little duplication, you think there's a much larger population just based on natural data and natural observance. Okay. So what are the assumptions of the Lincoln-Peterson estimator? Well, I mentioned already the population's assumed to be closed. You can violate that assumption, but you have to build more sophisticated models to do that. We assume that individuals in the first sample are identifiable in the second sample, that the bird doesn't lose its tag on its leg, for example. We assume equal capture probability for each member of the population within a capture period. They can differ by capture period. We might have a more likely chance to catch a fish on the second day than the first day or something like that. But we assume that at least within that capture period, every individual has the same capture probability. Okay. When we want to move toward more general models, we start to expand the ideas of these capture-recapture models. The first thing that we can do is say, well, we don't have to stop at 2 samples from the population. We could increase that to whatever number we wanted, provided that we have a reasonable basis to do the study in a reasonable amount of time to keep the closure assumption intact. So we usually let k be the number of capture periods, and when we generalize the model a bit more, we let pij be the probability that an individual I is captured in capture period j. So it's something that reflects an individual's capture probability during a particular capture period. And then an individual's capture history can be written as a vector of zeros and ones, where a 0 indicates lack of capture in a particular capture period, and a 1 indicates capture in that capture period. So for example, if we had 5 capture periods in a study and we saw an animal or an individual with a capture history of 01001, that would indicate that they were captured in the 2nd and 5th capture periods and not captured in the other 3. So if you play this out and try to build a statistical likelihood for your observance of your data and a likelihood of your model parameters as a function of that observed data, we have to define a little bit of notation. And I don't want to get unwieldy in the notation here, but what I do want to mention is that there are 2 to the k possible capture histories as identified by that vector, because every position in the vector could be 0 or 1. So there's 2 to the k possible outcomes, all but one of which are observable. You don't observe the number of animals that have the null vector because they were never captured. So those are the ones that we don't actually know about at the end of the study. But nevertheless, we know that every animal is either captured or uncaptured, so we actually can identify that number as just the population size, which we want to make inference about, minus the number that we actually saw during the study, which is what we've actually observed. So if I define omega as kind of a general term for the set of observable capture histories, and x of omega as the number of individuals with each of those capture histories, and p of omega kind of more generally as the probability that an individual has a particular capture history, and s as the number of individuals captured at least once during the study, so that we can have some notational simplicity, then the likelihood of the overall set of capture histories just follows a multinomial distribution. Basically, if you think of a multinomial distribution, you think of it kind of like a binomial where everything is either a success or a failure, out to everything not just being a success or failure, but being maybe in category 1 or 2 or 3 or 4 or 5 and so on. Okay? But there's a parallel between the multinomial and the binomial. You can think of the binomial distribution as a special case of the multinomial distribution with 2 possible categories. So if we write out the multinomial distribution, what we find is there's a combinatorics piece out front that involves the population size, which is what we want to make inference about. We've got the product of the individual probabilities of the capture histories raised to the power of the number of animals or individuals with those capture histories. And then we have a piece at the end that is the probability of not being captured at all during the study, and then raised to the power of the number of uncaptured individuals in the study as well. So this is a likelihood function that allows us to make inference about the probability of capture and the population size, which is ultimately what we want to know. The probability of capture is sort of a nuisance parameter in this sense. It needs to be estimated, but it's not necessarily our focus. Okay, so how would this work in practice for a real set of numbers? I guess if we had 3 capture periods, there would be 7 observable capture histories. And so just hypothetically, suppose for a minute that in these 7 capture histories here that could be observed, we had a number of individuals that would be, say, 7, 5, 8, 9, 10, 12, and 3. And that would lead to a total of 54 animals that are individuals that are captured at some point during the study. And so our likelihood function would involve an unknown population size, the sample sizes that we observe for each of the individual capture histories, the probabilities of those capture histories raised to powers associated with the numbers in each of those groups, and then finally this big bucket at the end that says the probability of not being captured at all raised to the number that were not captured at all, which does involve our target parameter of n. Okay, so I mentioned in the past slide we have to model capture probabilities somehow. We have to think about the probability of being captured and how that would be quantified. So there are a few different, there's lots of ways to do it, and part of the reason that this area of research has continued for so many years since the initial development is not just the increase in the number of capture periods, it's the complexity that you can introduce in terms of modeling individuals' behavior and capture probability. There's a large amount of potential research that you can do and continue to do in this area. Some relatively common approaches to modeling capture probabilities for closed populations might include a null model, which just says, let's assume that across every sample and across every individual, the capture probability is the same. And that's just some probability we call p, and we just go ahead with that, right? It's probably overly simplistic in a lot of cases, but it's certainly a workable, simplifying assumption. You might say, well, the different samples themselves would probably have different capture probabilities. I mean, if I'm fishing on one day versus another, maybe I stay longer on one day, maybe I put more effort in, maybe the things just go my way, maybe the fish or the animals or the individuals are behaving differently on that day. So individual samples may have different capture probabilities. And those are called time effects model. We say essentially that capture probabilities vary by sample, but within a sample, every individual has the same capture probability. Heterogeneity models, which is what we're going to focus on today, make what turns out to be a more complicated assumption. It says, well, individuals can differ with their capture probability, but essentially the capture probability isn't affected by time, right? So the different samples are all kind of the same. You're repeating the same process, but individuals vary. Some are easy to find, some are hard to find. That turns out to be pretty common in animal populations, right? There are lots of reasons why you can think of some animals being much more likely to be caught and captured than some others. Okay, size, age, proximity to where you started, all those kinds of things may be a factor in that heterogeneity. Okay. And then you can combine these effects if you want. You can build models with more than one of these effects. You can build models with 2 and even 3 of these effects all within the same general model. Yes?
Does that include the possibility that being recaptured is more likely than being captured the first time?
So I didn't mention that, but that would be called a behavioral effect. And yes, that is definitely another approach to that. And in fact, so behavioral effects mean, yes, like you said, being captured once affect your probability of recapture. So in most cases, that's thought to be a negative effect. But if being captured isn't really very onerous and maybe there's a small reward with it, there's actually been cases of even animal populations becoming what are called trap happy, where they're more likely to come back a second time. So that introduces a form of heterogeneity, but a form that is changing throughout the study. But yes, that's called a behavioral effect, and you can actually also throw that in as well. Good question. Okay, so we're going to focus on heterogeneity models because, as you'll see, that's been, or as I'll mention, that's been a significant problem through the years in terms of research. So, how do you model heterogeneity? It's relatively easy to see, I think, how you would model time effects. You would just set a different probability for each capture period, and then at least each individual in the population would have a probability that's pretty easy to figure out as far as how many times it's been captured or its capture history. But if the individual probabilities vary, that seems to make the problem more difficult because you need to know the probability of an individual being captured, which just makes it a lot harder. Okay. So mathematically, it's not, or from a modeling perspective, it's not the easiest thing to solve. But 2 really common approaches are, there have been more than these 2, but 2 common approaches that are used now are finite mixture models, where essentially we say, well, let's just take the homogeneity where everything's the same, but let's create different subgroups in the population, each of which has a probability of being in that subgroup, and each of which has its own but constant capture probability. So you're forcing groups to exist, each of which is homogeneous, but collectively they provide heterogeneity in the population. Okay? And usually you don't allow you don't have too many different groups. You can have more groups, but usually people find that 2-point or 3-point finite mixture models are appropriate for these kinds of situations. And by that I mean in a 2-group finite mixture model, you might say, well, some animals or some individuals are easy to find, some are hard to find, and we'll just let them vary as they will. And maybe if you go with 3 groups, you might have a low, a medium, and a high relative capture probability for those individuals. If you increase the number of groups, of course, you can end up getting pretty close to the point where everybody has their own capture probability, but that's a hard modeling question. So pi i is usually the probability of being in group I, and then theta I is the probability of being captured in group I. And so these parameters end up working their way into the capture probability. So if we have 3 capture periods in 2 groups, the probability of a 1-1-0 capture history of being captured the first 2 times and then not the third will be the probability of being in group 1. Oh, sorry, I forgot the subscript there. Oh yeah, there it is. Theta 1 squared, the probability of being captured twice. 1 minus theta 1, the probability of not being captured in the third period, and then if you're not in group 1 in a 2-group finite mixture, you're in group 2, so your probability of being in group 2 is 1 minus pi 1. Your capture probability of being captured twice is theta 2 squared, and you have a 1 minus theta 2 probability of being avoided in the third capture period. And so this, as I mentioned, creates heterogeneity at the population level, but homogeneity within each group. Other approaches have focused on continuous probability distributions, such as the beta distribution, which is a probability distribution that can be skewed or symmetric, and it can be skewed in either direction over the 0-1 interval. And so it allows a lot of flexibility in terms of the shape of capture probabilities across the population. This allows every individual to have their own capture probability, but they're drawn from a distribution that we want to make inferences about. Okay, so finite mixture versus continuous models. And then, well, I've probably turned this into a notational challenge here, but in statistics, we get some data reduction through a process called sufficiency, which means in some cases you'll write out a full likelihood and then you'll recognize, well, I can sort of summarize that likelihood so that 2 data sets with the same sufficient statistics would yield the same inference about the population parameter. a simple example of this is we don't always necessarily take a full data set to make inferences about the population mean. Most of the time we say, if you just give me the sample mean and maybe the sample standard deviation and a normal model, I can make an inference about the population mean. You don't have to tell me all of your data, just tell me the mean and the standard deviation and I'll go from there. That's sufficiency at work, and we get some of the same benefit here where we say, you know, it turns out, using this modeling structure, what we really need to know, since we're not focusing on time effects, is just the number of times an individual is captured. So I need to know the number of times an individual is captured exactly once, the number of individuals that are captured exactly twice, up through the number of individuals that are captured k times. And so we can use the same general likelihood function, but slightly simplify it for the fact that we have these sufficient statistics in place. Okay, so how do we model these probabilities? Well, if we're using a finite mixture distribution, it just turns out to be the probability of being captured L times, if you will, is just the sum over all the different groups of the probability of being in the group times the combinatorics-based probability of being captured that number of times. And then, this is probably smaller than you could read, but it turns out the probability under the beta distribution turns out to be a function of a combination and then the gamma function involving two parameters of the beta model that we've called alpha and beta, and the number of times an individual is captured. So there's a closed form expression for the probability of being captured a certain number of times, even when the data are assumed to come from a beta distribution. And that's called a beta binomial probability model. So what we do with each of these two models is we substitute them into the likelihood function that we've already evaluated, and then it's usually off to the races to evaluate the unknown parameters using a likelihood-based approach. Okay, now everything was going okay. We thought, you know, people were generally happy with heterogeneity models, and there was a well-known paper in 2003 that caused a bit of a problem in the field where it was written by, his name is William Link. He basically noted that there was a problem with these models in that two different models, say one a mixture model and one a continuous model, could fit the data equally well with regard to some model selection criteria, but give very different inferences about the population size. Non-reconcilable differences. You know, interval 1 over here, interval 2 over here. And he even illustrated this with a study, an example with 20 capture periods. And he said, look, even if you've done a whole bunch of captures, here's an example where things still are not working out and are not reconcilable. So his paper was about non-identifiability in the area, but essentially it just meant you're kind of forced, your inferences are based on the model you chose, and model selection criteria are not going to help you reconcile that difference, which is what we usually would have thought. We just let model selection criteria help you make the decision. You go from there. He said, no, that's not necessarily going to work. Here's an example. So it was definitely important research in the area. So we're left with that, maybe the thought that heterogeneity models aren't so good after all. Okay. Next, a brief mention of Bayesian modeling so that the simulation results will make sense when we talk about Bayesian models. So traditional statistics, frequentist statistics says and uses the likelihood-based approach that we've talked about previously. And essentially, if I boil that down to its spirit, it says the data are the thing that provide the inferences about the population parameters. That's it, just the data. What else would you go on? Okay. And frequentist-based statistics relies on a relative frequency definition of probability. The relative frequency of an event is its probability in the long run. Well, in a Bayesian world, when you use a Bayesian definition of probability, Bayesians define probability as uncertainty or lack of knowledge. And if you take that definition and use Bayes' rule with it, you recognize that there are lots of things that are fixed but that you don't know. And so you can reflect that lack of knowledge with a probability distribution. I could probably state my beliefs about, say, the proportion of left-handers on campus here. I have an idea that it's not 50%, it's not 85%, it's more likely to be 15 or 20% based on my life experience. So I could probably draw a probability distribution for the proportion of left-handers on campus that reflects my beliefs. And defining probability as uncertainty lets you do that, and that's what Bayesian statistics is essentially about. When you apply this definition, you get to do strange things like treat population parameters that are fixed as random variables with probability distributions. That's kind of a weird thing. The population mean's all of a sudden a random variable. Took me a while to get my head around that when I first learned about it. And so what you do in terms of Bayesian statistics is you say, well, instead of just letting the likelihood inform my conclusions, what I do is I do a three-step process, if you will. I define my beliefs about any parameter before I see the data. That's called a prior probability distribution. Then I observe the data, which have a likelihood under certain parameters. And then I use those, and I find what's called a posterior distribution, my beliefs about the parameter after I've seen the data. So the idea is that the posterior distribution, what you believe about the parameters after you've seen the data, is proportional to your prior beliefs times that likelihood function at that particular parameter value. Okay, the posterior is proportional to the prior times the likelihood. And here's a picture that helps illustrate that. What we essentially see here is, here's a hypothetical example where in my prior world over here on the left, I believed that the parameter was slightly negative, and I had a certain amount of uncertainty about that. But my data, which is over here in green, gave a likelihood function that was peaked slightly positive, right? It looks like maybe 2 or 3 was the most likely parameter value given the data in this hypothetical example. So my posterior is now just the blended version of those two beliefs. Right? I update my prior beliefs with the data to yield what I believe after the study is done. And that's the process of Bayesian inference. And essentially what would happen then in a Bayesian world is my posterior distribution from one study could become a prior distribution for a future study. It just reflects what I believe now. And I've become attracted to that line of thinking over time. I just have found that, without going into great detail, that I really enjoy the benefits of Bayesian statistical modeling. Okay, so what affects the posterior distribution? What affects your conclusions after a study? Well, the first thing is the prior distribution. If you have a prior distribution with low variance, that means I've got a strong prior belief. That means I'm pretty stuck in my ways about the parameter. The data aren't going to sway me that much, all other things being equal. On the other hand, if I have a highly variable or almost uniform prior distribution, it says I don't really know what to think, and I can express that ignorance with a prior distribution. And when I do, the data takes over and informs my conclusions. And the second thing, though, is, and sometimes, by the way, if you use a highly variable or nearly uniform prior, those are sometimes called, in general, non-informative prior distributions. Then there's the amount of data. If I observe a lot of data, it's going to overwhelm the prior no matter what I do. In the big data era, your prior is a drop in the bucket, so to speak, in most cases, and so your data take over and you get pulled in the direction of the likelihood function. Okay, and that's a good thing. A lot of data should be pretty compelling. Okay, so how does all this fit into a simulation approach that we wanted to study? So here's what, let's see, that's probably smaller than anybody would want to be able to read. Okay, let me explain. We wanted to look at the contradictory inference question, and we wanted to allow the sample size, the number of capture periods, to increase throughout the study to see how often these contradictory inferences happened, and also to look at how the different models performed under different data generating scenarios. So what did we look at? We allowed the simulated true population size to vary between 100 and 1,000, so we let it be 100, 500, or 1,000. We let the theoretical average capture probability be 5% or 10% across the population. We kept it relatively low because we felt like that would allow some of the differences in the models to manifest themselves a little more clearly, and we felt if they went too high that it might just, they might all end up at the same conclusion just because of our simulation approach. So we kept the capture probabilities relatively low. And then we generated data under the mixture assumptions, both 2-point and 3-point. And then we used 2 different continuous distributions to generate the data. We used a beta distribution and a logistic distribution to do that. And then we fit 3 different Bayesian models to each of the data sets that we generated. So we fit a 2-point mixture, 3-point mixture, and a Bayesian beta binomial model. And then furthermore, we let the number of capture periods vary from 6 up to 16 by 2. So we created a very large factorial design for ourselves, which took us a while computationally. There were 144 factor combinations minus the data fit. We had 25 data sets at each factor combination, and then we fit the 3 Bayesian models. The one thing I'll mention is we kept the prior distributions in the Bayesian models all relatively non-informative. So we used the Bayesian machinery, but in a very weak prior context, so that any prior opinion that we had very little influence on the conclusions. How did we look at the outcomes? Well, if we wanted to evaluate how well a model did, the first thing that we did is we looked at the population size estimate. If in a Bayesian world you have a posterior probability distribution for a parameter, you have to think a little bit about what you'd use as a point estimate. After all, you have a probability distribution, right? How do you summarize a probability distribution? Oftentimes we summarize it through central tendency using either a mean or a median. We chose the median of the posterior distribution of n as a single point estimator for the population size. We could have used the mean as well. There was some skewness in these distributions, these posterior distributions. We decided on the median to be more consistent with the distribution with skewness. Okay. And what we assessed are three things. We looked at how accurate were the estimates, and we used that through a relative bias where we didn't just measure the bias itself because we had different population sizes. So we looked at the bias on a percentage basis. We looked at the coverage probability and the length of a nominal 95% posterior, I forgot to mention, equal-tailed interval for the population size. We look at that posterior distribution. We looked at its 95% probability region from the 2.5th to the 97.5th percentiles, and we looked at whether that covered the true population size. And then we also looked at the length of that interval, right? So, you know, two intervals that cover the same value don't perform equally well. If one's narrower and it has equal coverage probability, that's better. Okay. And then lastly, we looked at whether the posterior intervals overlapped. So were they giving equal or contradictory inferences? Okay. So the simulation results will come through some graphics, and I'll have to point out the salient features of these because this is a nice two-factor interaction plot, which is great if you stare at it for a while, but it's not necessarily easily digested upon first glance, as I can attest to from reading it. So what I'm going to do is I'm going to point to the next page first, where we talk about what we see, and then I'll try to point back to where we see that in the graph in order to keep things fairly clear. What did we find here? Well, the first thing that we found is relative bias was actually higher for small population sizes. Where do we see that? We see that over here. The true population size, as it increased, our relative bias was a bit higher. As we increased up in terms of our simulated population size, the biases got lower. This red line was drawn at a 0% relative bias. So that's the target that you wanted to hit. Does that make sense? Yeah, being off by 5 or 10 makes a much bigger difference in a smaller population size than a bigger one. So that didn't surprise us too much. Mixture models turned out to be more robust when fit to continuous data than the beta binomial continuous fit model was to mixture data. So when you look at model misspecification, one of the things you look at is what happens if I choose the wrong model? How poorly do I do? So assessing the quality of the fit there was important. What we found was mixture models were more robust. I see that primarily over here. DGM was my term for data generating model, and so these were the data generated under the 4 different assumptions: beta, logistic, mixture, and mixture. And then the model fits are all plotted over here, and probably the biggest thing that you see is there was some significant negative bias down here, which indicates the beta binomial continuous model fits to mixture data. So the misspecification error rate was higher over there. Average capture probability didn't affect things all that much. We look over here. These are pretty consistent. They're not necessarily great, but they're pretty consistent from left to right. So that didn't make that big of a difference. And the, sorry, I went back one. The relative bias, was not affected much by the number of capture periods. This was somewhat surprising. We kind of figured maybe as we increased capture period numbers from 6 to 16, we'd do a lot better. That's pretty flat, and that was, I think initially when we looked at it, somewhat disappointing. I think we had expected it to do a lot better, and we were stymied a bit for a while and trying to figure out how to interpret that. But those were the findings there. Okay, let's look at coverage probabilities, right? I mean, bias is one thing, but maybe the interval captures the real value a certain percentage of the time, and we're happy with that. Well, what we see here is I've drawn a red line at the nominal 95% that we would want a 95% probability interval to have, right? I want something with a 95% nominal statement to work 95% of the time. Okay, well, how did we do here? We'll again do the conclusions and then back to point at the features of the graph. Coverage probabilities dropped with the true population size, except for the 3-point mixture model. So what you notice here is as we got to larger and larger population sizes, that beta binomial model fit coverage probability was dropping off. So was the 2-point mixture model, but the 3-point mixture model was hanging in there and doing pretty well. That was a good sign for that model. And I think I mentioned that second point there. Average capture probability didn't change things all that much. The rates tended to stay about the same. There was a little increase from high to low, but not a whole lot of, back to the last one, sorry. Not a whole lot of change from here to here, but a little bit of one. But what we also notice is as K was increasing, as the number of capture periods were increasing, our coverage probabilities were also dropping. So the problem that Link talked about in his paper, where as you get more information in some of these models, you're actually converging but possibly to the incorrect answer, was also showing up in our data. That was also, I think, worthy of some explanation, right? So some concern. Not drastic. I mean, you know, these aren't even going as low as maybe 80%, so it's not horrendous, but the fact that they're dropping as you get more information is a bit concerning in some ways. Okay. Well, what about posterior interval length, right? What's the length of the interval doing? And what we noticed first and foremost is the interval's wider when the population size is bigger, which makes sense because for larger populations you certainly need a wider interval in most cases to capture the true population parameter. Let's see, I don't see a whole lot here and here, but we also noticed that probably the coverage probabilities were dropping because the certainty, the precision was increasing with these intervals. The intervals were getting narrower as we increased the number of capture periods in the study. Okay? So the bad news is we weren't performing as well from a confidence perspective. We had biases that were not necessarily going away, although oddly enough they were a little positive in many cases. So it almost indicates that we were certainly, but not very accurately, slightly overestimating the population size. Okay. Is that what we wanted? No. Collectively, though, I think if you look at it that way, you might think of that as not being that bad. We're a little high in these models, and collectively. But we're doing it with maybe a little bit of a false sense of precision. Okay, so I won't repeat these overall results. I'll just repeat what we kind of found collectively. We thought the 3-point mixture model performed the best. So we felt like that did the best out of the 3 models. The posterior interval length was widest, but its bias and coverage probability were the best of the 3 models. The 2-point mixture model did okay, but it had some coverage probability dropping as the increase in number of capture periods happened, and so we had some concerns there. And then I think we found that the beta binomial Bayesian model did not perform as well. It essentially didn't do as well under model misspecification as the mixture models did. And in some sense, that makes sense. I think if we look at our simulations, although we generated data under the beta model and logistic model, I think that at our lower capture probabilities that we had, I think a 2- and 3-point mixture model were probably better set up to succeed in that scenario than a beta model, which forces capture probabilities to exist all the way between 0 and 1. Okay. And increasing the number of capture periods didn't really result in the improvement that we thought. So that was kind of the worst part of the simulation results that we had were those. That, you know, we weren't, there was no optimal answer that we said, well, voila, we found it, and y'all can stop talking, you know, with research is done, right? We found that there's probably continued research that can be done. But what was the good news? The good news, well, perhaps the good news for the practitioner is that you don't need 16 capture periods for your study to necessarily improve your results, right? I mean, someone has to actually carry these out, and they're people who have real data to gather, so I think, you know, we can tell them to get by with less. That's not all bad. But the best news, I think, that we found was that the contradictory inference rate wasn't too bad. And I'll explain what I meant there. What we did is we looked at the 95% posterior intervals from each of the models for the population size. And we just measured how often do all 3 of the intervals overlap each other, pairwise, right? So how often do all 3 of them overlap? How often do 2 of them overlap? How often do 1 of them overlap? And how often are they all off in their own space, completely contradictory of each other? Okay. Because Link's example had an example where 2 different models completely did not overlap, and that was one of the main causes for concern. So we reported the percentage of overlaps, actually. And the good news is, even in the worst possible cases, we had pretty high rates of everything overlapping. At 16 capture periods, this was the worst result we saw. We still had 95% of data sets had all 3 intervals overlapping. There wasn't a single contradictory inference in the bunch. At larger population sizes, we still had almost 95% of the data sets having all 3 of the intervals overlapping. Now, asking 2 intervals to overlap isn't a high bar to clear, but it certainly, I think, gives you a sense that 2 models aren't completely disagreeing with each other. So we found a good percentage there, and these were the worst results that we saw. At high capture probabilities, 97% of the data sets had all 3 of the intervals overlapping, and even in other cases, we still had very high percentages of the data sets with all the intervals overlapping. And I went through and cherry-picked. These were the worst results I could find in the study. So the good news was this contradictory inference problem didn't seem to be showing up too much. Okay? And in fact, we never found a case where the intervals were all completely off in their own space. We always had at least one overlap in the simulation. So from our original concern, we thought, okay, this is not the first research that's been done to compare these model fits with each other, or these types of model fits. There have been other simulations, and simulations, to be fair, always have a certain weakness. And I think the weakness is that your conclusions are restricted to the conditions under which you studied them. And we always need to be pretty careful with that. It's easy for someone like me to say, well, we did a simulation and here's what we found. We did a simulation for these conditions. There are lots of others we could do. We could have the capture probabilities be higher, for example. We could have different population sizes, much smaller or much larger. There's lots of other things we could vary. So I hate to make sweeping conclusions, but what we felt was, based on our simulation, concern about contradictory inferences shouldn't be too terribly high. If you're a practitioner in this field, and you feel like the model selection criteria are not going to help you make that decision, you don't have to be unduly worried that the model that you're going to choose is going to lead you to a completely opposite conclusion of some other model. They're probably going to agree, at least somewhat, and in fact, you could report the results of 2 different models and say, even if they differ a little bit, here's how they differ. But you don't have to worry that you're going to be getting 2 things that are in a completely different domain almost. Okay, so that was probably the best news of the simulation. I think the thing that we found made a nice take-home message. Okay, so in conclusion, this is just a short history of capture-recapture models in relatively recent times. There's a lot of literature on this topic that goes back quite a while. But these are the papers that we reference the most heavily, and we certainly appreciate you being here on a Friday and listening to a talk about animal and individual populations. Thank you.
Indication that you don't need 16
right.
Captures. Is there a way to find an optimal?
We were looking for, I would have hoped in our simulation we would have found some kind of optimal number. But I think what we found is that it's impossible to do that without the absence of some other information. So for me, looking at how certain do I want to be about where the population size is one thing. And I think we can see that your certainty is certain. Your intervals are getting narrower, but you have to balance that with a little bit of a sense of that coverage probabilities may be dropping off. Now, one thing I didn't mention very well, though, is that the mixture model did pretty well in coverage probability. It just tended to be wider. So I think a lot of the common sense things that we see, I would say that a practitioner would probably want to be balancing the need for precision and acceptance of a little higher error rate with the need to be right and making a more general statement about the population. So it would depend on context and the specific example. Yes?
So this study that Link or whatever did that came out with this question, yeah. I mean, are the types of models and data collection that they were concerned with incorporated in here specifically? And then, like, I mean, so it seems like, oh, this is a real worry now that we've kind of been reassured here.
Yeah.
But I guess I'm trying to wrap my head around why at the time was it considered such such a word. I mean, like, certainly
Yeah.
if you take two specific examples and someone cherry picks
Right.
somewhere, like, you know,
Right.
okay, you can definitely find it.
Right. So I think a few things on that. Prior to his paper, there were different approaches to modeling heterogeneity, which was a hard problem to begin with. And I think, you know, I was doing some of my PhD research at around the time where this paper came out. So I kind of remember it as, well, there's always different statistical models, but, you know, in theory, with large enough data sets, they all generally converge to similar answers. I mean, that's an oversimplification, but it's an easy line of thinking to fall into, right? And so all of a sudden, I remember one member of my committee said, you know, this paper just came out, you really got to read this. You know, it's probably going to affect a bit of what you're working on, which is what a PhD student wants to hear. Immediately, right? Great, you know. So it was concerning, I think, from the sense that the models weren't all converging to the same answer. And he gave an example of it with a really large number of capture periods, but I think his point was that when you have a decent chunk of the population that is virtually uncatchable, your fit and your model selection criteria are heavily influenced by the assumption of the capture probability distribution. And so I think that was his essential finding, was the assumptions that you make are going to drive your inference. And that was why it was a big concern, because everyone said, well, these are all approximations anyway. How do I know which one's best? And that's probably a large part of why the paper was really important. So I don't think it was just a diabolical example that showed up, I guess.
So in some sense, I mean, what you've shown here kind of supports that idea, right? Because I mean, you're saying that as you increase the number of capture periods, the interval is narrowing. You're also dropping off the coverage probability.
Right.
So I'm not that surprised that these two models may predict things that are far apart, because they could both not be covering. It's not unlikely. It's not unlikely that they both fail to cover then the actual the actual mean or whatever it is you're looking at.
I agree. We were, and again, we didn't set the bar that high. Two intervals overlapping is not a grand agreement necessarily. If they overlap just over here, I mean, you'd say they probably disagree. And we may have been able to come up with a measure that was better than that in terms of you know, agreement or disagreement. But we were at least pleasantly surprised, given these results, that most of the time the models at least have some level of agreement. But it does not appear, I mean, Link's work shows that the different models are not always going to converge to the same answer. And you sort of have to live with that in these heterogeneity models. But I think the one thing that you know, thinking statistically, you still want to estimate things using models even if you don't think that the model works to perfection, because some information and some inference that's reasonably accurate is probably better than no information at all, right? Even if it doesn't necessarily meet some of the criteria that you're saying it's supposed to meet, like 95% coverage. Yeah.
So you're talking about a lot of abstract things.
Yeah.
In terms of like practical, I want to know how many fish are in my lake.
Right.
When you say that they don't agree, relative to the size of the population, is that a big number or a small number? Just order of magnitude sorts of issues. So I have 5,000 fish in my lake. Right. And these are estimating it at 4,900 and 5,100. To me, that's not a big difference, even if they don't overlap.
Right, so maybe the difference in the center points of the intervals or the difference in the end points of the intervals. You're right, we did not look at that because we were looking at it at a macro scale. How often are they just going to disagree? But we did not measure the magnitude to which they disagreed. My look at the data suggested that what happened was that the beta binomial model was sometimes too certain and too precise, but not necessarily that far off from the truth. So, you know, in a case of 100, the beta binomial model sometimes went from, you know, like 85 to 95, which you would say isn't that bad, but it wasn't, you know, 100 in some cases. And then the mixture models did tend to be wider. So we looked at a couple real data analyses, which I didn't talk about here, but we had some increase in capture period real data set studies, and what we found essentially were the mixture models were staying really wide but accurate, and the beta binomial model was honing in on something that wasn't too inaccurate, but was technically, you know, in some cases too low. okay, or a little bit off. So you're right in that that is kind of, you know, I think underemphasized at this point. Okay.
Any other questions?
Other questions?
All right, let's thank our
Okay,
speakers.
thank you.